There is something deeply unsettling about a clear night sky, and most people never notice it. Not because of what is there, because of what is not. Look up on any night far from city lights, and you will see a ceiling of fire. Thousands of points of light scattered in every direction, ancient and cold and impossibly distant. The human eye reads it as random. A chaotic spray of embers across a black canvas. But randomness is not what you are looking at. The universe is not random. It is structured, violently, almost geometrically structured. And the architecture of that structure, the reason galaxies exist where they do, the reason matter clumps and clusters and forms filaments hundreds of millions of light years long instead of spreading out like smoke, that question is one of the most profound in all of science. It took humanity thousands of years to even ask it correctly. So why does the universe look the way it does? Not the color of stars, not the number of planets, the shape, the large-scale geometry of matter itself across a volume so enormous that the word large becomes almost offensive in its inadequacy. Right now, if you could pull back, not just out of Earth's atmosphere, not just out of the solar system, not just out of the Milky Way, but truly pull back to a scale where entire galaxies are smaller than dust specks, you would see something that looks nothing like random scattering. You would see a web. Scientists call it the cosmic web. It is the largest known structure in existence, a three-dimensional network of filaments, walls, and nodes made of billions of galaxies, stretched across a region roughly 93 billion light-years in diameter, which is the observable universe. The portion of reality whose light has had enough time to reach us since the beginning. 1 light-year is approximately 9.5 trillion kilometers. The observable universe spans 93 billion of those. If you were to drive at highway speed, 100 kilometers per hour, from one side of the observable universe to the other, you would need roughly 100 trillion years. The current age of the universe is about 13.8 billion years. You would not make it. And across that entire expanse, matter is not spread evenly. It is threaded. The filaments of the cosmic web are made predominantly of a substance that cannot be seen, cannot be touched, and does not interact with light in any way detectable by the human eye or by any telescope ever built. Dark matter. It comprises roughly 27% of the total energy content of the universe compared to the ordinary matter, atoms, molecules, stars, planets, you, which makes up approximately 5%. The rest is dark energy, the mysterious repulsive force accelerating the universe's expansion. The universe is, in the most literal physical sense, mostly made of things we cannot directly observe. The filaments and nodes of dark matter act as a gravitational skeleton. Ordinary matter, gas, dust, stars, falls into the gravitational wells carved by this invisible scaffolding. Galaxies form at the densest intersections. Clusters of galaxies accumulate where filaments cross. The great voids, regions of space hundreds of millions of light years across that contain almost nothing, sit between the filaments like bubbles in foam. The largest known void, sometimes called the Bhuta's void, spans approximately 330 million light years. If the Milky Way were located at its center, astronomers on Earth would not have discovered the existence of other galaxies until the 1980s, because the nearest neighboring galaxy would be so far away that its light would be imperceptibly faint through 20th century instruments. The structure is staggering, but it raises the immediate question that science cannot let go of. Where did the pattern come from? Here is what the physics actually says. The universe, in its earliest measurable moments, specifically during the first fractions of a second after the event known as the Big Bang, was not perfectly uniform. It was almost uniform. The temperature and density of the primordial plasma that filled all of space were nearly identical in every direction. But not quite. There were microscopic fluctuations, quantum-level variations in density, so small they dwarf anything we can engineer today in terms of precision. These were not random in the colloquial sense. They were quantum mechanical fluctuations, governed by probabilistic laws that have since been confirmed to extraordinary accuracy. Those tiny wrinkles in the fabric of the early universe, density variations on the order of 1 part in 100,000, were the seeds. Gravity, slow and patient and absolutely relentless, did the rest. Over hundreds of millions of years, regions slightly denser than their surroundings pulled in more matter. That matter increased the density further. More matter followed. Eventually, the density was high enough for hydrogen gas to collapse under its own gravity and ignite nuclear fusion. The first stars were born. Around 300 to 500 million years after the Big Bang, before any planet existed anywhere in the universe. And here is where a popular misconception collapses under the weight of the actual data. Many people imagine the Big Bang as an explosion, a single point of matter hurled outward into an empty, pre-existing space, the way a bomb detonates in a room. This mental image is entirely wrong, and the wrongness matters because it shapes how people misunderstand the universe's origin and structure. The Big Bang was not an explosion of matter into space. It was an expansion of space itself. There was no pre-existing void for matter to fly into. There was no center point from which everything burst outward. Every location in the universe was, at the moment of the Big Bang, the same location. Space and time themselves originated in that event. The universe did not appear inside something else. The something else did not exist. This distinction is not semantic. It is physically consequential. Because if the Big Bang were a conventional explosion, we would expect matter to be distributed like shrapnel, denser at the center, thinner at the edges, with a definable origin point. We observe none of that. In every direction astronomers look, to the limits of what instruments can detect, the large-scale structure of the universe appears roughly the same. No center, no edge, no privileged direction. The universe, at the largest scales, is homogeneous and isotropic. Those are the technical terms. They mean the same in composition everywhere and the same in every direction you look. This is called the cosmological principle, and it is one of the foundational assumptions of modern cosmology, one that has been tested repeatedly against observation and has held. The cosmic microwave background radiation is the most direct evidence. It is the light left over from roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time, allowing photons to travel freely instead of being constantly scattered. That ancient light now permeates all of space, cooled by the universe's expansion to a temperature of approximately 2.7 degrees Kelvin, just barely above absolute zero. The European Space Agency's Planck satellite, which completed its observations in 2013, mapped this radiation across the entire sky with unprecedented precision. What Planck revealed was a temperature map of the infant universe. The variations in that map, the tiny hot and cold spots, correspond to the density fluctuations that eventually grew, through gravity, into the cosmic web. The seeds of every galaxy, every star, every planet in the observable universe are visible in that map. The pattern of the largest structure in existence was written into the universe before a single atom of hydrogen had ever fused into helium. The universe looks the way it does because it remembers where it came from. That memory is encoded in light. Light that has been traveling for over 13 billion years. Light that bathes every square centimeter of space, including the air around you right now, carrying the imprint of the universe's first breath. But remembering where it came from only answers part of the question. The density fluctuations explain why matter clumped. They do not explain why space itself took the geometry it did. Why the universe is flat, not curved inward like a sphere, not curved outward like a saddle, but geometrically flat to within the precision limits of every instrument humanity has ever built. That particular fact points directly toward one of the most counterintuitive episodes in the early universe's history. An episode so extreme, so brief, and so consequential that it stretches the boundaries of what any physicist is comfortable calling understood. The answer lives in the first fraction of the first second, and it will change how you see everything you think you know about the beginning of time. The universe was once smaller than a proton, not metaphorically, not as a thought experiment. In the current best-supported models of cosmological physics, all the energy that today comprises every galaxy, every star, every atom of hydrogen drifting in the space between galaxy clusters, all of it was once compressed into a region smaller than a single subatomic particle. The density at that moment exceeded anything that can be produced in a laboratory by a factor so large that no unit of measurement used in everyday physics applies cleanly. The temperature was not merely hot in the way a star is hot. It was a condition in which the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have existed as a single unified interaction, indistinguishable from one another. That is where the story of the universe's shape begins. Not with galaxies, not with stars, with a state of matter and energy that physics can approach mathematically, but cannot yet fully describe. The standard cosmological model, known as lambda CDM, where lambda refers to the cosmological constant governing dark energy and CDM stands for cold dark matter, is the framework that best matches all available observational data. It is not a guess. It is built on decades of independent measurements, galaxy surveys, gravitational lensing data, the precise temperature fluctuations of the cosmic microwave background, the observed abundances of light elements like helium and deuterium, and the measured expansion rate of the universe. Every one of these independent lines of evidence converges on the same picture, and that picture has a problem embedded in it, a problem so severe that for decades it threatened to unravel the entire framework. It is called the horizon problem. The cosmic microwave background, the ancient light released roughly 380,000 years after the Big Bang, is almost perfectly uniform across the sky. When the Planck satellite measured it, the temperature of that radiation varied by only about 1 part in 100,000 across the entire celestial sphere. Whether you look toward the constellation Orion or directly opposite it, toward the southern sky or the northern pole, the temperature of the CMB is approximately 2.725 degrees Kelvin. The difference between the hottest and coldest spots is less than 0.03 of a thousandth of a degree. That uniformity sounds reassuring. It sounds like things should be smooth, but it is, in fact, deeply disturbing to anyone who thinks carefully about causality. Two regions on opposite sides of the observable sky are separated by roughly 93 billion light-years. Given the finite speed of light, 300,000 kilometers per second, and the age of the universe at the time the CMB was released, those two regions had never been in causal contact with each other. No signal, no heat exchange, no physical interaction of any kind could have traveled between them in the time available. They were, in the most rigorous physical sense, completely isolated from each other. Yet they have the same temperature, to 1 part in 100,000. Think about what that means in everyday terms. Imagine two isolated communities on opposite sides of a planet with no history of contact, no shared technology, no communication whatsoever, and finding that both communities independently invented the same measurement system, accurate to 5 decimal places. The probability of that happening by chance is not low, it is essentially 0. For the universe to be that uniform without any mechanism to establish uniformity, it would require initial conditions so precisely fine-tuned as to be physically implausible. The universe would have had to begin in a state of near-perfect thermal equilibrium across regions that could not, by any standard physics, have ever reached equilibrium. This is not a minor theoretical discomfort. It is a fundamental breakdown in the explanatory power of the standard Big Bang model as originally formulated. The horizon problem sat in the middle of cosmology like a fracture in the foundation of a building. Invisible from a distance, catastrophic up close. It was not the only one. The flatness problem compounds the difficulty. Measurements of the universe's geometry, derived from the precise angular spacing of temperature fluctuations in the CMB, first established rigorously by the boomerang balloon experiment in 2000 and confirmed and refined by the WMAP and Planck satellites, show that the universe is geometrically flat to within the measurement precision of the best instruments humanity has built. The density of the universe is extraordinarily close to what cosmologists call the critical density, the exact value at which the universe is neither curved inward toward an eventual collapse nor curved outward toward unbounded expansion, but balanced on the geometric knife edge between the two. The ratio of the universe's actual density to the critical density is called omega. Planck measurements place omega at approximately 1.000, with an uncertainty in the last decimal places. Flat. The problem is that flatness is an unstable equilibrium in the equations governing cosmic evolution. Just as a pencil balanced on its tip will fall if displaced by even the tiniest fraction, a universe that begins with a density even slightly above or below critical will deviate further and further from flatness as time passes. For the universe to be as flat as it is today, after 13.8 billion years of evolution, the density of the early universe would have had to match the critical density to within 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros in the denominator. No known physical principle in the standard Big Bang framework explains why the universe would begin in that condition. 2 independent, severe, structural problems. Both pointing to the same conclusion, the standard Big Bang model, taken alone, is incomplete. The resolution to both problems arrived not from observation, but from theory. In 1980, the American physicist Alan Guth, then a postdoctoral researcher, published a paper proposing that the very early universe underwent a period of extraordinarily rapid exponential expansion, a fraction of a second after the Big Bang, before a single proton had fully formed. He called it inflation. The numbers involved are not easy to hold in the mind. During inflation, the universe is theorized to have expanded by a factor of at least 10 to the power of 26, that is, 1 followed by 26 zeros, in a time interval of approximately 10 to the negative 32 seconds. 100 million trillion trillionths of a second. The expansion was not matter moving through space. Space itself expanded, carrying whatever it contained along with it at a rate far exceeding the speed of light. This does not violate special relativity, which prohibits objects moving through space faster than light, because the expansion of space itself is not governed by that constraint. To understand what inflation does to the horizon and flatness problems, consider the following. Before inflation, the region that would eventually become the entire observable universe was extraordinarily small enough that all parts of it were in causal contact, able to exchange heat and reach thermal equilibrium. Inflation then stretched that tiny, thermalized region to a size vastly larger than the observable universe. Every part of the sky we can see today originated from that single, causally connected patch. The uniformity of the CMB is not a coincidence. It is a fossil of the thermal equilibrium that existed before inflation erased the boundaries. The flatness problem dissolves by the same mechanism. Inflation takes any initial curvature and stretches it until it becomes, locally, indistinguishable from flat, the same way the surface of the Earth appears flat to someone standing on it, even though the planet is a sphere. The larger the sphere, the flatter any local patch appears. Inflation made the universe so enormous that its curvature, whatever it originally was, became immeasurably small. Guth's original model had mathematical inconsistencies that required refinement. Andre Linde, and separately Andreas Albrecht and Paul Steinhardt, developed revised models in 1982 that resolved those issues. The inflationary framework has since been extended, debated, and tested against data in ways that Guth could not have anticipated in 1980. The most powerful test came in 2014, when the BICEP 2 telescope at the South Pole announced a detection of a specific pattern in the polarization of the CMB, a swirling signal called B-mode polarization, which would have been direct evidence of gravitational waves produced during inflation. The announcement generated extraordinary excitement in the physics community. Within months, the signal was reanalyzed. Planck data revealed that the pattern detected by BICEP 2 was consistent with polarized emission from interstellar dust in the Milky Way, not primordial gravitational waves. The detection did not hold. Inflation remains the most powerful and well-supported solution to the horizon and flatness problems, but direct observational proof of it, the kind that would close the debate, has not yet arrived. The theoretical framework predicts a background of primordial gravitational waves imprinted on the CMB polarization. Future experiments, including the Simons Observatory in the Atacama Desert of Chile and the planned CMB S4 project, are designed specifically to detect that signal at sensitivity levels an order of magnitude beyond what BICEP 2 achieved. The universe's shape was written in an instant too brief to measure and a scale too small to see. And the evidence for it is encoded in light that is older than every star currently burning in the sky. What inflation also predicts, and this is the detail that keeps physicists awake at night, is that the quantum fluctuations present during that exponential expansion were not erased. They were stretched, magnified from the subatomic to the cosmic. Those fluctuations became the density variations that seeded the cosmic web. The structure of everything that exists, every galaxy, every star, every rocky world, traces its origin back to quantum mechanical uncertainty during a period of expansion that lasted less time than it takes light to cross the width of a single proton. Quantum mechanics wrote the blueprint. Inflation printed it at cosmic scale. Gravity spent the next 13 billion years building from it. But inflation, for all its explanatory power, opens a door that has no visible end. Because if inflation happened once, if the conditions that drove it were embedded in the physics of the very early universe, there is no obvious reason why it happened only here, only once, only producing one universe with one set of physical constants. The mathematics of inflation, in its most general form, predicts that it does not stop cleanly everywhere at the same moment. In most regions of space, inflation ends and a universe like ours forms. But in other regions, quantum fluctuations cause inflation to continue. Those regions expand faster than the regions where inflation has ended, generating new volumes of space, potentially with different physical constants, different particle masses, different values of the cosmological constant. This process, known as eternal inflation, does not terminate. It produces an infinite, ever-branching structure of separate regions, each a universe unto itself. A multiverse, not as science fiction, as a direct mathematical consequence of the equations governing inflation. Whether the multiverse is real physics or a theoretical artifact is one of the most contentious open questions in all of cosmology. Because here lies the edge of what observation can, even in principle, reach. No signal from a separate inflationary bubble can ever cross the space between it and our universe in a finite time. The concept may be, by the strictest definition of the word, untestable. And yet the equations produce it, insistently, repeatedly. Across multiple independent formulations of inflationary theory, the universe that looks so vast from Earth may not be a universe at all. It may be one condensation in an ocean of condensations, each separated by a volume of space still inflating, still expanding, still unreachable by any instrument, any signal, any observer. The question of why the universe looks the way it does has, in less than a century of physics, become something far larger than the question it started as. And embedded in the fabric of our own sky, in the precise temperature of light more than 13 billion years old, is a set of numbers that either confirm the most extraordinary mechanism in physics, or point towards something we have not yet thought to look for. The quantum fluctuations that inflation magnified did not produce a perfectly smooth universe. They produced a universe with a specific statistical pattern of density variations, a pattern with a precise mathematical signature. That signature has been measured. And what it reveals about the content of the universe forces a confrontation with the most destabilizing fact in modern physics. That is the share of the universe made of the same material as everything you have ever seen, touched, measured, or built an instrument to detect. Every star, every planet, every ocean, every human being, every atom of oxygen pulled into a lung, every iron nucleus forged in the core of a dying star, every molecule of water that has cycled through the atmosphere of this planet for 4.5 billion years. All of it, every piece of ordinary matter described by the standard model of particle physics, every element on the periodic table, accounts for approximately 5% of the total energy content of the universe. The rest is not empty space. Empty space does not have the gravitational effects that astronomers measure. The rest is something else entirely. Roughly 27% of the universe is dark matter. Another 68% is dark energy. Together, these two quantities, neither of which has ever been directly detected in a laboratory, neither of which corresponds to any confirmed particle in the standard model, dominate the structure and fate of everything that exists. The visible universe, The part that emits or reflects light and fills every astronomy textbook ever printed is a thin foam on the surface of a much deeper ocean. The evidence for dark matter is not theoretical speculation. It is observational, and it comes from multiple completely independent lines of measurement that converge on the same conclusion with a consistency that leaves no serious scientific room for doubt. The first major observational signal came from rotation curves. A galaxy rotating under gravity should behave the way planets orbit the sun. Objects farther from the center should move more slowly, because the gravitational pull weakens with distance. This is a direct consequence of Newton's law of gravitation and is confirmed in the solar system to extraordinary precision. Mercury moves at approximately 47 kilometers per second in its orbit, while Neptune moves at approximately 5.5. The further out, the slower. In the 1960s and 70s, the American astronomer Vera Rubin, working with her colleague Kent Ford, made precise measurements of the rotational velocities of stars and gas at different distances from the centers of spiral galaxies. The instruments required for this work had only recently become sensitive enough to measure the Doppler shifts of light from the outer regions of galaxies with the necessary precision. What Rubin and Ford found was not a gradual decline in rotational velocity with distance from the galactic center. The rotation curves were flat. Stars at the outer edges of galaxies were moving just as fast as stars much closer to the center. In some cases, at velocities that, given only the visible mass of the galaxy, should have been physically impossible. At those speeds, the stars should have been flung outward, escaping the galaxy's gravitational hold entirely. They were not escaping. They were held. The only physically consistent explanation was that each galaxy was embedded in an enormous halo of mass that could not be seen. Mass that extended far beyond the visible disk of stars and gas, providing the gravitational force necessary to keep the outer stars bound. The mass inferred from the rotation curves was several times larger than the mass that could be accounted for by all the visible matter in the galaxy combined. The dark matter halo was not a minor correction. It was the dominant gravitational structure. Rubin's results were initially met with skepticism. They were replicated across dozens of galaxies, then hundreds. The rotation curves were flat every time. The conclusion became inescapable. Gravitational lensing provided an entirely independent confirmation. Einstein's general theory of relativity, published in 1915 and 16, predicts that mass curves spacetime, and that light traveling near a massive object will follow the curvature of spacetime, bending its path in a way that can be observed as a distortion of background sources. The more mass, the more bending. Astronomers can measure the total mass of a cluster of galaxies by observing how severely it bends the light of galaxies behind it, producing arcs, rings, and multiple images of the same background source. When this total gravitational mass is compared to the mass of all visible matter in the cluster, all the stars, all the gas detected in X-ray observations, the visible matter accounts for only a fraction of the total. The rest is dark matter, distributed in a halo around and between the cluster galaxies, invisible but gravitationally unambiguous. The most dramatic single demonstration of dark matter's reality came from a system called the bullet cluster, the result of two galaxy clusters that collided and passed through each other approximately 150 million light-years from Earth. During the collision, the hot gas that makes up the majority of ordinary matter in galaxy clusters, detectable in X-ray wavelengths, was slowed by electromagnetic interactions and piled up between the two clusters, visible as a bright region in X-ray observations made by the Chandra X-ray Observatory. The galaxies themselves, being largely collisionless, passed through each other relatively undisturbed. The dark matter halos, mapped through gravitational lensing, also passed through each other, remaining associated with the galaxies rather than the gas. The result was a spatial separation between where the ordinary matter ended up, the X-ray bright central region, and where the gravitational mass ended up, coinciding with the galaxies. If dark matter did not exist and gravity were modified to explain galactic rotation curves without invoking new mass, the gravitational lensing signal should have remained centered on the gas. It did not. The mass and the light were in different places. The bullet cluster is, in the assessment of most cosmologists, The single most direct empirical evidence that dark matter is a real, physical substance separate from ordinary matter. What dark matter actually is remains one of the most pressing unsolved problems in physics. The leading candidate for most of the past 4 decades has been a class of hypothetical particles called WIMPs, weakly interacting massive particles. A WIMP would have a mass somewhere between a few times and a few thousand times the mass of a proton, would interact with ordinary matter only through gravity and the weak nuclear force, and would have been produced in thermal equilibrium with the hot plasma of the early universe before freezing out as the universe cooled. The predicted relic abundance of WIMPs from thermal freeze-out matches the observed dark matter density with a precision that physicists found deeply compelling, a coincidence sometimes called the WIMP miracle. Decades of experiments designed to detect WIMPs directly have found nothing. The Large Underground Xenon experiment, operating in a mine nearly 1,500 meters below the surface of South Dakota to shield it from cosmic ray backgrounds, completed its final run with no confirmed WIMP signal. Its successor, Lux Zeppelin, operating in the same facility with a liquid xenon target of 10 tons and sensitivity more than an order of magnitude beyond its predecessor, has also reported no detection as of its most recent published results. The parameter space in which WIMPs were expected to exist, mass and interaction cross-section, has been compressed by these null results to a region that many physicists now consider physically implausible. WIMP dark matter has not been ruled out, but it has been cornered. Other candidates have gained attention as a result. Axions, extremely light particles originally proposed in 1977 by Roberto Peccei and Helen Quinn to solve a separate problem in quantum chromodynamics, the theory of the strong nuclear force, would interact with ordinary matter so weakly that detecting them requires instruments of extraordinary sensitivity. The Axion dark matter experiment at the University of Washington and its successor ADMX-G2 search for axions by looking for their conversion into microwave photons in a strong magnetic field. No confirmed detection yet. Sterile neutrinos, primordial black holes, ultralight scalar fields. The range of dark matter candidates that remain theoretically viable and observationally unconstrained is a direct reflection of how little is known about the dominant form of matter in the universe. Dark energy presents an even deeper problem. In 1998, 2 independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were using Type Ia supernovae as standard candles to measure the expansion rate of the universe at different epochs in its history. Type Ia supernovae occur when a white dwarf in a binary system accretes enough mass to exceed the Chandrasekhar limit, approximately 1.4 times the mass of the Sun, and undergoes a thermonuclear detonation. Because the trigger mechanism involves a fixed mass threshold, the peak luminosity of Type Ia supernovae is nearly uniform across the universe, allowing astronomers to calculate their distance from their apparent brightness with considerable precision. The expectation, based on the physics of a universe filled with matter and radiation, was that the expansion of the universe should be decelerating. Gravity pulls matter together. A universe expanding after the Big Bang should expand more and more slowly as gravity works against the expansion over time, the way a ball thrown upward slows as it rises. The supernovae did not show deceleration. The distant supernovae were fainter than they should have been if the universe's expansion were slowing. Fainter meant farther. Farther at a given redshift meant the universe had expanded more than expected between then and now. The expansion of the universe was not decelerating, it was accelerating. Something was pushing space apart, overcoming the gravitational attraction of all the matter in the universe and driving galaxies away from each other at an ever-increasing rate. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for this discovery. The agent responsible for the acceleration is called dark energy. In the simplest model, it corresponds to the cosmological constant lambda, the term Einstein introduced into his field equations in 1917 and later called his greatest blunder, believing a static universe required it, then abandoned after Hubble's discovery of cosmic expansion. Dark energy, in this model, is a property of space itself, a fixed energy density that does not dilute as space expands. As the universe grows, The total amount of dark energy grows with it, while the density of matter dilutes. Eventually, and this is the current trajectory of the observable universe, dark energy dominates completely, and the expansion accelerates without limit. The theoretical problem with dark energy is severe. Quantum field theory predicts that the vacuum of space should have an enormous energy density due to quantum fluctuations, virtual particles constantly appearing and annihilating throughout all of space. The predicted value of this vacuum energy, calculated from quantum field theory, is approximately 10 to the power of 120 times larger than the observed value of the cosmological constant, 10 to the power of 120. That is not a small discrepancy. It is the largest known discrepancy between a theoretical prediction and an observation in the history of science. It is called the cosmological constant problem, and it remains completely unresolved. No mechanism has been found that naturally suppresses the quantum vacuum energy to the observed value. No extension of the standard model, no version of supersymmetry, no string theory compactification has produced a clean solution. The universe is accelerating. The cause is real and measured. The explanation does not exist. Embedded in the flatness of the universe, in the web of filaments built on invisible scaffolding, in the accelerating expansion driven by something that no experiment has ever isolated or identified, is a set of physical facts that the most advanced theoretical frameworks humanity has constructed cannot yet fully account for. The architecture of the cosmos is built from materials that remain, after decades of the most sophisticated experimental physics ever attempted, almost entirely unknown. And the density fluctuations that inflation stamped onto this dark scaffolding, the quantum seeds that became the cosmic web, carry within them a statistical signature so precise that it encodes not just the history of the universe, but the physical conditions of its very first moments. Reading that signature requires an instrument pointed not outward into deep space, but backward in time, to light released when the universe was less than 400,000 years old. That light contains a set of acoustic oscillations, pressure waves that traveled through the primordial plasma at more than half the speed of sound, whose pattern, frozen into the CMB at the moment of recombination, is one of the most information-dense signals in all of observational astronomy. The physics of those waves reveals something that changes the entire picture of what the universe is made of. And it comes from a direction nobody expected. Sound shaped the universe. Not sound in the way the word is commonly understood. Not pressure waves traveling through air, not vibrations perceptible to a human ear. The universe, for the first 380,000 years of its existence, was not filled with air. It was filled with a plasma, a superheated opaque sea of protons, electrons, and photons so densely packed and energetically coupled that light could not travel freely through it. A photon emitted in one location would be absorbed and re-emitted almost immediately, trapped in a continuous scattering process that made the early universe as impenetrable to light as the interior of the sun is today. But plasma transmits pressure waves, and the early universe was full of them. The quantum density fluctuations seeded by inflation created regions of slightly higher and lower density throughout the primordial plasma. Gravity pulled matter inward toward the denser regions. Radiation pressure, the outward push of the trapped photons, resisted that compression and pushed back. The result was an oscillation. Regions of plasma compressed, reached maximum density, rebounded outward, reached maximum rarefaction, and compressed again, in a cycle governed by the competing forces of gravity and radiation pressure. These were sound waves, in the precise physical sense, longitudinal pressure oscillations propagating through a medium. Their speed was not the 340 meters per second of sound in air at sea level. In the primordial plasma, the speed of sound was approximately 57% of the speed of light, roughly 170,000 kilometers per second. These waves propagated outward from every density perturbation simultaneously, across the entire universe for 380,000 years. Then, abruptly, they stopped. At approximately 380,000 years after the Big Bang, the universe had cooled enough to around 3,000 degrees Kelvin for protons and electrons to combine into neutral hydrogen atoms for the first time. This event is called recombination, a term that is slightly misleading since the electrons and protons had never previously been combined, but the name has persisted. When neutral atoms formed, the photons that had been tightly coupled to the plasma were suddenly free to travel. The universe became transparent. The radiation that was released at that moment is the cosmic microwave background, the oldest light in the observable universe. When the photons decoupled from the matter, the radiation pressure that had been driving the acoustic oscillations vanished instantly. The sound waves froze. Every oscillation that had been in progress at the moment of recombination stopped exactly where it was, its pattern imprinted permanently into the distribution of matter. The waves did not fade gradually. They halted in a single moment, crystallized into the spatial distribution of baryonic matter, ordinary atoms, across the universe. The distance a sound wave could have traveled in 380,000 years at the speed of sound in the primordial plasma is a fixed physical scale. It is called the sound horizon, and it measures approximately 490 million light-years in today's expanded universe. That distance is not arbitrary. It is a ruler, a standard length scale imprinted into the large-scale structure of the universe with extraordinary precision. The prediction follows directly from the physics. If acoustic oscillations shape the early distribution of matter, galaxies today should show a statistical preference for being separated by distances corresponding to the sound horizon. Not a wall of galaxies at that distance. The effect is subtle, a gentle excess probability, but measurable. The measurement came in 2005. The Sloan Digital Sky Survey had by that point mapped the positions of nearly 200,000 galaxies across a significant fraction of the sky, with redshift measurements precise enough to determine their three-dimensional positions. Daniel Eisenstein and his colleagues analyzed the correlation function of those galaxies, a statistical measure of how often pairs of galaxies are separated by a given distance, and found exactly what the acoustic oscillation physics predicted. A clear excess of galaxy pairs at a separation of approximately 490 million light-years, a bump in the data. Clean, statistically significant, and precisely where the theory said it should be. This feature is called the Baryon Acoustic Oscillation Peak, commonly abbreviated BAO. Its detection was not merely a confirmation of a theoretical prediction. It was the first direct observational evidence that the acoustic physics of the primordial plasma had left a measurable imprint on the distribution of galaxies across the modern universe. The sound waves of the infant cosmos are visible today in the spacing of galaxy clusters, frozen into the fabric of the large-scale structure, like the rings of a stone dropped into water, preserved for 13 billion years. The implications reach further than structure. Because the sound horizon is a known physical scale, calculable from first principles using the measured temperature of the CMB, the speed of sound in the primordial plasma, and the age of the universe at recombination, it functions as a standard ruler. By measuring the apparent angular size of the BAO feature in galaxy surveys at different redshifts, cosmologists can independently measure the expansion history of the universe. A ruler of known physical length, observed at a known distance, subtends a predictable angle. If the observed angle differs from the prediction, the expansion history must be revised. BAO measurements have since been made by multiple independent surveys: the 2DF Galaxy Redshift Survey, the Wiggle-Z Dark Energy Survey, the Baryon Oscillation Spectroscopic Survey known as BOSS, and its extension eBOSS, across a wide range of cosmic epochs. Together, they provide one of the most powerful independent constraints on the nature of dark energy, and they consistently return results compatible with the cosmological constant. Dark energy appears to be uniform in space and constant in time, behaving exactly as Einstein's lambda predicts. This is simultaneously reassuring and deeply unsatisfying. Reassuring because the simplest model fits the data. Unsatisfying because the simplest model provides no physical explanation for why the cosmological constant has the value it does. A separate and more recent development has sharpened that dissatisfaction considerably. The expansion rate of the universe today is described by a quantity called the Hubble constant, denoted h0. It measures how fast the universe is expanding per unit distance, conventionally expressed in kilometers per second per megaparsec, where 1 megaparsec equals approximately 3.3 million light-years. For decades, measuring H0 precisely was one of the central problems in observational cosmology, with different methods producing results that differed by enough to be scientifically uncomfortable. By the early 21st century, two independent approaches had reached sufficient precision to make the disagreement impossible to ignore. The first approach uses the early universe. From the precise measurements of the CMB, particularly the Planck satellite data released in 2013, 2015, and 2018, cosmologists can calculate the Hubble constant by fitting the entire lambda CDM model to the CMB power spectrum. The Planck result gives H0 as approximately 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. The second approach uses the late universe. Astronomers build what is called the cosmic distance ladder, a chain of overlapping distance measurement techniques, each calibrated against the previous, extending progressively further into space. The first rung is geometric, parallax measurements of nearby stars, now performed with extraordinary precision by the European Space Agency's Gaia satellite. The second rung uses Cepheid variable stars, pulsating stars whose luminosity varies with a period directly related to their intrinsic brightness, a relationship discovered by Henrietta Swan Leavitt in 1912. By measuring the period of a Cepheid and applying Leavitt's law, the star's true luminosity can be determined, and from the apparent brightness, its distance. Cepheids are used to calibrate the distances to nearby galaxies hosting Type Ia supernovae, which then extend the ladder to cosmological distances. The SH0ES project, Supernovae H0 for the equation of state, led by Adam Rees using Hubble Space Telescope and later James Webb Space Telescope data to measure Cepheids with unprecedented precision, obtains H0 as approximately 73 kilometers per second per megaparsec, 67.4 versus 73. The two numbers are incompatible within their stated uncertainties. The discrepancy is now at approximately 5 sigma, the same statistical threshold used to claim the discovery of the Higgs boson at CERN. In particle physics, 5 sigma is discovery. In cosmology, applied to a tension between two well-established measurements, it means something is deeply wrong with the current understanding. This is called the Hubble tension, and it is the most significant unresolved crisis in cosmology today. The possibilities are uncomfortable in different ways. If the Planck measurement is correct, and the distance ladder is biased by some systematic error not yet identified, an error that has survived extensive independent cross-checks, including verification by the James Webb Space Telescope, then decades of careful distance measurements are compromised in a way that has not been located despite intensive searching. If the distance ladder is correct and the CMB-derived value is wrong, then the lambda CDM model itself is incomplete or incorrect, and the standard cosmological framework requires revision at a fundamental level. A third possibility is the most radical. Both measurements are correct, and the discrepancy reflects new physics, a dark energy that is not constant but evolves with time. An extra species of relativistic particles in the early universe that altered the sound horizon, a modification of gravity on cosmological scales. Early dark energy, a component that existed at high densities in the early universe and then diluted away, has been proposed as a solution, but it introduces new parameters that require their own fine-tuning and creates tensions with other observational constraints. The James Webb Space Telescope, operational since 2022, has provided Cepheid measurements of sharpness and precision impossible from the ground or from the Hubble Space Telescope's older instruments. Rather than resolving the tension, the Webb data published by the SH0ES team in 2023 confirmed the higher value of the Hubble constant with improved precision. The tension did not shrink. It held. In 2024, the Dark Energy Spectroscopic Instrument, DC, released its first-year BAO results from a survey mapping tens of millions of galaxies, the most precise BAO measurement ever made. The DC data showed hints that dark energy may not be perfectly constant, that its equation of state may be evolving slowly with time. The statistical significance of this signal in the first-year data release was not sufficient to constitute a definitive detection, but it was consistent enough across multiple independent analyses within the DESI dataset to generate serious attention from the theoretical community. Further data releases from DESI, covering larger volumes and more galaxies, are ongoing. The acoustic oscillations of the early universe, a phenomenon operating on scales of hundreds of millions of light years, traceable to quantum fluctuations in the first fraction of a second, have become one of the sharpest tools in observational cosmology. They are a calibration standard written into the universe itself, requiring no laboratory to construct and no instrument to create. They were there before any star existed, propagating through a plasma that filled all of space, driven by physics that operated identically everywhere in the observable universe simultaneously. They also carry, encoded in their statistical properties, the seeds of an answer to a question that has grown steadily more urgent as the precision of measurements has increased. The universe's expansion is accelerating. The cause is unidentified. The rate of that expansion, measured from two independent directions, gives two different answers. And the pattern of galaxy clustering that acoustic oscillations produced may be showing the first statistical tremors of something changing. A dark energy that is not constant, a cosmological landscape that is not static, a universe whose ultimate fate may be different from what the simplest current model predicts. The frozen sound of the early universe is still speaking, and what it is saying is becoming harder to reconcile with what the oldest light in the sky appears to confirm. Something does not fit, and the place where it does not fit is not at the edge of the data. It is at the center. The universe is dying, slowly, methodically, and by its own physical laws. Not in any way that threatens a human life or a civilization or even the geological timescale of a rocky planet. The death of the universe operates on intervals so vast that the entire current age of the cosmos, 13.8 billion years, would not register as a measurable fraction of the time remaining before the last stars extinguish. But the trajectory is established, the physics is unambiguous, and the agent responsible is the same invisible force that Perlmutter, Schmidt, and Rees detected in the brightness of distant supernovae in 1998. Dark energy, driving the accelerating expansion of space, pulling the universe apart at scales that grow larger with every passing billion years. To understand what that means concretely, consider the structure of the observable universe right now. The Milky Way is gravitationally bound to a collection of roughly 80 galaxies known as the local group, which spans approximately 10 million light-years. The local group is itself falling toward a larger concentration, the Virgo cluster, a dense aggregation of more than 1,300 galaxies, approximately 53 million light-years away. The Virgo cluster sits at the center of a broader structure called the Virgo supercluster, also known as Laniakea, a gravitationally coherent supercluster spanning approximately 520 million light-years and containing the mass of roughly 100 million billion suns. Laniakea itself is one node in the cosmic web, one intersection in a filament system that stretches across the entire observable universe. All of this structure, the local group, the Virgo cluster, Laniakea, the filaments, exists because gravity, acting over billions of years, has assembled matter into these concentrations faster than the expansion of space has been able to pull them apart. In the dense regions of the cosmic web, gravity wins. The galaxies within the local group are not receding from each other. The Milky Way and the Andromeda Galaxy, Messier 31, are approaching each other at approximately 110 kilometers per second and are expected to begin merging in approximately 4.5 billion years. But beyond the gravitationally bound structures, expansion dominates, and it is accelerating. Galaxies outside the local group are receding. The further away they are, the faster they recede. Not because they are moving through space at high velocities, but because space itself is expanding between us and them, adding distance at a rate proportional to the separation. For galaxies close enough, peculiar velocities, the actual motion of galaxies through space due to local gravitational interactions, can partially or fully offset the recession. For galaxies beyond a certain distance, the recession velocity due to expansion exceeds the speed of light. Not because anything is moving faster than light, but because the expansion of space is not governed by the relativistic speed limit that applies to objects moving through space. The boundary beyond which galaxies are receding faster than light can travel toward us is called the Hubble sphere. It lies at a distance of approximately 14.3 billion light-years. Galaxies beyond that boundary are, at this moment, moving away from us faster than any signal we could send will ever catch them. They are not merely distant. They are permanently unreachable, not by any limitation of technology, but by the geometry of an accelerating universe. This is already true of the majority of the observable universe. The observable universe, the sphere within which light has had time to reach us since the Big Bang, has a radius of approximately 46.5 billion light-years. The Hubble sphere has a radius of approximately 14.3 billion light-years. Every galaxy currently outside the Hubble sphere is already beyond permanent causal reach. As dark energy continues to drive accelerated expansion, the Hubble sphere itself will eventually stop growing. Galaxies that are today just inside the reachable boundary will cross outside it. The number of galaxies observable from the Milky Way will decrease over time, not because the galaxies cease to exist, but because the light they emit will never bridge the expanding gap between us and them. In approximately 150 billion years, roughly 10 times the current age of the universe, nearly all galaxies outside the local group will have receded beyond the cosmological horizon. The night sky of any civilization that might exist at that epoch would contain only the merged remnant of the local group galaxies, surrounded by a void. The cosmic web, the filaments, the clusters, all of it will be invisible and unreachable, not because it will have been destroyed, but because expansion will have carried it beyond the boundary of causality. A civilization born at that epoch, studying the sky with any instrument imaginable, would have no observational evidence that the universe contained anything beyond their local galaxy. They would have no CMB to measure. It will have redshifted to wavelengths so long as to be undetectable with any plausible instrument. They would have no distant supernovae to reveal cosmic acceleration. The evidence that allowed 20th and 21st century astronomers to reconstruct the history and structure of the universe will have been erased by the very process those astronomers discovered. Humanity exists at an extraordinarily privileged moment in cosmic time. The evidence is still here. The CMB is still measurable. The distant galaxies are still visible. The BAO signal is still accessible in galaxy surveys. The window during which the full architecture of the universe can be read from within it is finite, and by cosmic standards, it is nearly closed. The long-term future of the universe, governed by dark energy, proceeds through a sequence of astrophysical eras whose timescales dwarf anything in the current epoch. The stelliferous era, the age of stars, extends from approximately 10 million years after the Big Bang to roughly 100 trillion years from now. During this era, hydrogen gas continues to be converted into stars through gravitational collapse, nuclear fusion burns in stellar cores, and the universe continues to produce light. The current epoch sits roughly in the middle of this era. The Milky Way still has sufficient gas reserves to form new stars for several billion more years, though the rate of star formation across the universe peaked approximately 10 billion years ago and has been declining ever since. The universe is, by the measure of star formation rate, already past its most productive period. After the last low-mass red dwarf stars exhaust their hydrogen fuel, at timescales of approximately 10 trillion to 100 trillion years, the stelliferous era ends. No new stars form. The stellar remnants, white dwarfs, neutron stars, black holes, persist, but they produce no fusion energy. The universe enters the degenerate era, dominated by the slow cooling of white dwarfs over timescales of quadrillions to quintillions of years. Eventually, proton decay, if it occurs at the rate predicted by some grand unified theories, with a half-life on the order of 10 to the 34th years, will dissolve the ordinary matter in white dwarfs and neutron stars into radiation and lighter particles. The solid objects of the universe will evaporate, not through any dramatic explosion, but through the slow statistical process of proton instability. Current experimental limits from detectors like Superchemiokande in Japan place the proton lifetime at greater than 10 to the 34 years for certain decay modes, meaning proton decay, if it occurs, operates on timescales at least an order of magnitude beyond the current age of the universe multiplied by 1 trillion. Black holes dominate the subsequent era. Having consumed matter through accretion and merged with other black holes over the preceding eras, supermassive black holes will be the dominant structures in the universe. They will not persist forever. Stephen Hawking's theoretical work in 1974 demonstrated that black holes radiate energy through a quantum mechanical process at their event horizons. a phenomenon called Hawking radiation. The temperature of this radiation is inversely proportional to the mass of the black hole. Smaller black holes radiate faster and hotter, larger ones radiate slower and cooler. A black hole with the mass of the Sun would take approximately 2 times 10 to the 67 years to evaporate completely through Hawking radiation. A supermassive black hole with 1 billion solar masses would require approximately 2 times 10 to the 83 years. At the end of that process, the black hole does not leave behind a remnant. The final stages of evaporation release the remaining mass energy as a burst of high-energy radiation, a last thermal flash from the most massive objects the universe ever produced. After that, nothing remains but a thin, cold sea of photons, neutrinos, electrons, and positrons, spreading outward through a space that is expanding without limit, growing colder and more dilute with every passing eon. This endpoint is called the heat death of the universe, or more precisely, the state of maximum entropy. It is not a dramatic termination. It is an asymptotic approach toward thermodynamic equilibrium, a state in which no temperature differences exist anywhere in the universe. No gradients of any kind remain to drive physical processes, and no work can be extracted from any interaction. The laws of thermodynamics, specifically the second law, entropy in a closed system tends to increase toward a maximum, point toward this end with mathematical inevitability, given the physics currently understood to govern the universe. The timeline from the Big Bang to heat death spans approximately 10 to the power of 100 years. The current age of the universe is 13.8 billion years, roughly 10 to the power of 10. The distance between where the universe is now and where it is going is not 10 times larger, not 1,000 times larger. It is incomprehensibly, asymmetrically larger. The entire history of the cosmos to this point is, on the full timeline, less than the first page of the first chapter of a library containing every book ever written. And yet, within this brief window, on a rocky planet orbiting an unremarkable star in the outer regions of one spiral galaxy among 2 trillion, a species developed the capacity to read the CMB, map the cosmic web, detect the acceleration of expansion, measure the sound horizon of the primordial plasma, and calculate the timescale of black hole evaporation. To look at a universe composed 95% of unknown substances and derive its age, geometry, composition, and ultimate fate from the light still reaching its eyes. The James Webb Space Telescope is currently observing galaxies that formed within the first few 100 million years after the Big Bang. Galaxies whose light has been traveling for over 13 billion years before entering Webb's gold-coated mirrors. Among the most distant confirmed objects observed by Webb is a galaxy designated JADES GS Z140, with a spectroscopic redshift of 14.32, corresponding to a time when the universe was approximately 290 million years old. At that epoch, the universe had existed for barely 2% of its current age. The galaxy is already forming stars, already assembling structure, already obeying the gravitational blueprint written by inflation and acoustic oscillations hundreds of millions of years before its first star ignited. The universe is consistent. The physics that governed the primordial plasma operates in the galaxies Webb observes at the edge of the observable volume. The same gravitational constant, the same speed of light, the same quantum mechanical rules. Across 13.8 billion years of cosmic time and 93 billion light-years of space, the laws have not changed. That consistency is not obvious. It did not have to be that way. The values of the fundamental constants, the strength of gravity, the mass of the electron, the fine structure constant governing electromagnetic interactions, are what they are, and they are the same everywhere in the observable universe. A universe in which those constants varied with location or time would be structurally incoherent. Stars could not form. Chemistry could not occur. The conditions for complexity of any kind would not exist. Whether those constants are fixed by some deeper principle not yet understood, whether they are different in other regions of an inflationary multiverse, whether they were selected by some mechanism or simply happen to permit complexity in this particular condensation of inflated space. These are questions that current physics cannot answer. They may not be answerable by any conceivable extension of current physics. What is answerable? What has been answered with instruments, mathematics, and observation is the shape of the universe we inhabit. Flat. Dark matter dominated on the scale of galaxies. Dark energy dominated on the scale of the cosmos. Acoustic in its large-scale structure. Inflationary in its origin. Accelerating in its expansion. And finite in the window of time during which its full history can be read by any observer within it. The universe looks the way it does because of what happened in the first fraction of the first second. Because quantum fluctuations were stretched to cosmic scales, because dark matter provided the gravitational skeleton, because acoustic oscillations froze into the fabric of matter, because dark energy began to dominate when the density of matter diluted below a critical threshold, roughly 5 billion years ago, tipping the expansion from deceleration into the acceleration that continues today. Every photon in the CMB, every galaxy in the Sloan survey, every supernova measured by Reese and Perlmutter, every Cepheid observed by Webb, all of it is a piece of the same coherent picture. A picture assembled over a century of observation, from Henrietta Leavitt's photographic plates to Webb's infrared detectors, from Einstein's field equations to the DESI fiber array mapping tens of millions of galaxies across a quarter of the sky. The picture is not complete. The Hubble tension is real. Dark matter has not been identified. Dark energy has not been explained. The cosmological constant problem remains unsolved. The physics of inflation cannot yet be directly confirmed. But the outline is there. Vast, cold, accelerating, and indifferent to the questions being asked of it. And the asking continues. 13.8 billion years ago, there was no space, no time, no darkness waiting to be filled, because the concept of waiting requires time, and time did not yet exist. The Big Bang was not an event that happened inside the universe. It was the event from which the universe, including the space-time that gives events a location and a sequence, emerged. Everything that followed was physics. Unbroken, consistent, indifferent physics, operating across every scale from the subatomic to the cosmological without exception, without pause, without any moment in the intervening 13 billion years during which the laws changed or faltered. That continuity is not a small thing. The proton has the same mass in the Andromeda Galaxy as it does in the Milky Way. The speed of light measured in a laboratory in Geneva is the same speed carried by a photon that left a galaxy 12 billion years ago and arrived at the mirror of the James Webb Space Telescope last year. The fine structure constant, the dimensionless number governing the strength of electromagnetic interactions, approximately 1 divided by 137, has been measured in the absorption spectra of quasars at redshifts above 6, corresponding to a time when the universe was less than 1 billion years old. It matches the laboratory value to the precision limits of the measurement. The universe is not just large, it is lawful. Everywhere. Always. That lawfulness is what made the science in this documentary possible. Without it, the CMB temperature fluctuations measured by Planck would be uninterpretable. They could tell us nothing about initial conditions, because those conditions might have been governed by different physics. Without it, the BAO standard ruler would not be a ruler at all. The sound horizon depends on a speed of sound that depends on physical constants that would need to be identical in the early universe and in the universe today. Without it, type Ia supernovae could not function as standard candles across billions of light years because the nuclear physics of the Chandrasekhar limit would not be consistent across cosmic time. Every measurement described in this documentary rests on the assumption that physics is universal. And every measurement made has confirmed that assumption at every distance and every epoch accessible to observation. This is the first and most fundamental thing the universe has told us about itself. The second is that it had a beginning, not in the philosophical or theological sense, but in the precisely measurable sense. There exists a finite time in the past before which the observable universe, as currently understood, did not exist in its present form. The expansion of space, run backward through the equations of general relativity, converges toward a state of extreme density and temperature approximately 13.8 billion years ago. The light travel distance to the CMB, the oldest directly observable radiation, is approximately 45 billion light-years, and the CMB carries a detailed record of the universe's physical state at 380,000 years of age. These are not extrapolations from incomplete data. They are the result of multiple independent measurements, expansion rates, elemental abundances, structure formation, all converging on the same number. The universe is not eternal in the past. It has a history, and that history is readable. The third thing, and the one that sits most uncomfortably at the intersection of physics and philosophy, is that the universe we can observe is almost certainly not all there is. Inflation, in its most general mathematical form, produces more universe than any single observer can see. The quantum fluctuations during inflation that generated our CMB were local to a region that became our observable universe, but the inflationary field did not terminate everywhere simultaneously. Other regions continued inflating, producing space at a rate that outpaced any causal connection between them and us. Whether those regions contain different physics, different constants, different outcomes of symmetry-breaking transitions in the early universe, these are questions that cannot be answered from within our observable volume. The multiverse is not a hypothesis designed for comfort. No physicist proposed it to resolve a philosophical problem or to provide a sense of cosmic significance. It emerged, uninvited, from the mathematics of the most successful solution to the horizon and flatness problems that were themselves discovered through careful observational work. It is a consequence, not a premise. And because it may be untestable in any direct sense, it places a hard boundary on what science can claim to know. The universe beyond our cosmological horizon is, by the strictest definition, outside the domain of empirical verification. The laws of physics that we have verified within the observable universe may extend beyond it, or they may not. The data cannot reach us. That boundary is not a failure of science. It is a discovery. Science located its own horizon. It found the edge of what measurement can access, identified why that edge exists, the finite speed of light combined with a finite age of the universe combined with an accelerating expansion, and described the physics of what lies beyond that edge as rigorously as the mathematics allows, while acknowledging that the description cannot be verified. That combination of precision and honesty is not a weakness. It is the defining characteristic of the scientific method applied at full extension. The Hubble tension, the cosmological constant problem, the unidentified nature of dark matter and dark energy. These are not signs that physics has failed. They are signs that physics is working. A framework that produced no anomalies, no tensions, no unresolved parameters would not be advancing. Every precisely measured discrepancy is a signal. Every unexplained constant is a direction. Every null result in a WIMP detector narrows the parameter space and pushes toward the answer. The LX Zeppelin result that found no WIMPs is as scientifically valuable in its own way as a positive detection would have been. It eliminated a region of possibility that can now be set aside. Science does not move by confirmation alone. It moves by elimination, by precision, by the accumulation of constraints that gradually force the answer into a smaller and smaller space until only one possibility remains. The current state of cosmology is a state of productive, well-defined tension, a field that knows precisely where it does not understand, which is the necessary precondition for eventually understanding it. What has been understood, definitively, reproducibly, independently confirmed across multiple methods and multiple observatories on multiple continents and in space, is the following. The universe began in a state of extreme density and temperature approximately 13.8 billion years ago. An exponential expansion in the first fraction of the first second, inflation, smoothed the geometry to flatness, established causal coherence across what would become the observable universe, and stretched quantum fluctuations to the scales that seeded all subsequent structure. The universe filled with a hot plasma of protons, electrons, and photons. Acoustic oscillations propagated through that plasma for 380,000 years. When the plasma cooled enough for neutral hydrogen to form, the photons decoupled, the sound waves froze, and the universe became transparent. The pattern of those frozen waves is visible today in the CMB and in the statistical distribution of galaxies across the cosmic web. Gravity amplified the density fluctuations over hundreds of millions of years, collapsing gas into the first stars. Those stars forged heavier elements in their cores and dispersed them through supernovae. Subsequent generations of stars, enriched by those elements, formed planetary systems. Dark matter, distributed in halos around galaxies, provided the gravitational framework without which the structures visible in deep-field images would not exist. Approximately 5 billion years ago, the density of matter diluted below the threshold at which dark energy, a property of space itself, or something functionally equivalent, began to dominate, tipping the expansion from deceleration into acceleration. The acceleration continues today and will continue indefinitely under current physics, carrying the universe toward a cold, dark, maximally entropic endpoint on a timescale of approximately 10 to the power of 100 years. Within that timeline, on a planet 4.5 billion years old, orbiting a star halfway through its 10 billion year main sequence lifetime, in the outer regions of a galaxy containing between 100 billion and 400 billion stars, among an estimated 2 trillion galaxies in the observable universe. Within all of that, a pattern of chemistry produced nervous systems capable of modeling physical reality. Those nervous systems built instruments. The instruments measured the CMB to 1 part in 100,000. They mapped hundreds of millions of galaxies in 3 dimensions. They observed supernovae at cosmological distances and found that the universe was accelerating. They detected gravitational waves from merging black holes and neutron stars. They imaged the shadow of a black hole 400 million times the mass of the Sun, 55 million light-years away, in the galaxy Messier 87. None of that was inevitable. The emergence of complexity, of chemistry, of biology, of cognition, required a universe with the specific values of the fundamental constants that this universe has. A slightly stronger gravitational constant, and stars burn out before planets can form complex chemistry. A slightly weaker strong nuclear force and protons do not fuse in stellar cores. A slightly larger cosmological constant, and the universe expands too fast for gravity to assemble any structure at all. The observed values sit in a narrow range compatible with the existence of complexity. Whether that reflects a deeper principle of physics, a selection effect in a multiverse of varying constants, or simply the universe as it happens to be, this question has no current answer. What the question has is a questioner. That fact, that the universe produced from the physics of the primordial plasma, from the gravitational collapse of hydrogen, from the nuclear furnaces of stars, from the chemistry of carbon and water and phosphorus, entities capable of asking why the universe looks the way it does, is itself a datum, not a mystical one, a physical one. The universe is not merely lawful. Under its own laws, operating without direction, it produced the capacity to discover those laws. The CMB photon that left the last scattering surface 380,000 years after the Big Bang traveled for 13.4 billion years through expanding space and entered the detector of the Planck satellite in 2009. That photon carried information. Information about the temperature of the plasma it last scattered from. Information about the density fluctuations present at recombination. Information that, decoded by the mathematics of cosmology, revealed the age, geometry, composition, and origin of the universe it had been traveling through since before any star existed. The universe encoded its own history in light. The light traveled, and something was here to read it. That is not a coincidence science can currently explain. It is the outermost boundary of what the physics covered in this documentary reaches, and the first coordinate of whatever physics comes next. The questions that remain are not signs that the universe is unknowable. They are the exact shape of what is still to be known. The Hubble tension points somewhere. The cosmological constant problem points somewhere. The identity of dark matter points somewhere. Each unresolved tension in the data is a vector, a direction of inquiry with a specific, measurable target at its end. Future instruments will aim at those targets with sensitivity that current technology cannot achieve. The Vera C. Rubin Observatory, conducting the legacy survey of space and time, will map tens of billions of galaxies over a decade. The Nancy Grace Roman Space Telescope will perform deep, wide-field surveys in infrared light, unreachable from the ground. The next generation of CMB experiments, CMB S4, will measure the polarization of the oldest light in the universe with a sensitivity that may finally detect or definitively exclude the primordial gravitational wave signal of inflation. The answers are not here yet, but the instruments are being built. The mathematics is being written. The measurements are being designed with the specific anomalies in mind, the exact places where the current picture does not fully close. The universe is 13.8 billion years old. The first modern scientific description of its large-scale structure was published less than 100 years ago. The CMB was discovered 60 years ago. Dark energy was discovered 27 years ago. The first direct image of a black hole was taken 6 years ago. The science is not old, it is barely started, and the light is still arriving.